CallPaly's significant memory footprint can be addressed with optimization techniques, but it still doesn't scale well since you can use it with HNSW search. Now, let's look at an approach called Muvera, which unlocks HNSW search for multivectors and addresses CallPaly's finer measure flow. Let's go! The idea behind Muvera is to convert variable length sequences of vectors into fixed dimensional embeddings, making it possible to use the same approximate methods like we use for regular dense vector search. CallPaly can't be used with HNSW search because there is no way to build the HNSW index that powers approximate nearest neighbor search for asymmetric similarity measure like maxsim. As a result, CallPaly requires a brute force search technique that takes linear time. If you want to search 1 million documents with CallPaly, you need to calculate 1 million maxims. Muvera approaches that differently by converting sequences of vectors into highly dimensional single vector embeddings. That enables the use of HNSW. HNSW instead scales in logarithmic time, scaling easily to millions or billions of documents. It makes it more practical than original multi-vector representations. Let's review the steps required to implement that technique. The Muvera algorithm is based on a few steps. First of all, it aims to perform a clustering algorithm on the multi-vector embeddings, and the Muvera paper suggests using locality-sensitive hashing method, namely SimHash. Assume each of our tokens is mapped to a vector space, in our case two-dimensional. SimHash will then generate some random hyperplanes, splitting that space into two parts. Each vector will end up on one of the sides as defined by the hyperplane. However, one hyperplane is just not enough. SimHash will generate k hyperplanes, dividing the space into 2 to the power of k buckets. We can assign binary strings to each of these buckets by using either 0 or 1 to indicate the fact of being on either side of the corresponding hyperplane. The length of the bucket ID will be exactly k, in terms of the bits used. In our case, it's just 2, meaning there are exactly 4 different buckets, as that's how many value you can represent using 2 bits. After assigning buckets to each of the input token embeddings, we group the terms belonging to the same cluster together. SimHash aims to reduce the variable length of the sequences by finding some representative vectors for each of the buckets. Document and query processing is slightly different. In the case of documents, SimHash will take an average of all the token vectors belonging to a particular cluster. Since some of the buckets might be empty, it will also fill them with the value assigned to the closest non-empty cluster in terms of the Hamming distance. Just to give you an intuition, the Hamming distance will be equal to 1 between the cluster IDs that differ by just 1 bit. At the very end of that process, each of the clusters will have a single vector representing it. That means no matter how many input vectors you had, you will always end up with 2 to the power of k representative vectors. Query processing is slightly different. Instead of taking an average, you sum all the vectors in the same cluster. This means that the resulting vectors will have larger magnitudes for clusters with more vectors assigned. The idea is that it preserves the natural distribution of query terms, which can be beneficial for retrieval. Unlike with documents, you do not fill empty clusters for queries. Queries are typically shorter than documents, so it's more likely that some clusters will be empty. Filling them could introduce noise and distort their presentation, as each term would contribute to the dot product multiple times. So, if there were no tokens in a particular cluster, it will be represented as a 0 vector. No matter if you process documents or queries, you now have a single 128-dimensional vector for each cluster created by the SimHash procedure. 128-dimensional, as it's the most typical length of a single vector in multi-vector representations. Quite often, the number of hyperplanes in the SimHash procedure is set to at least 5, giving us 32 clusters. That's 4096 dimensions in total. Quite a lot. The distances between the vectors are the most important thing for semantic search. When you work with data in a very high dimensional space, it becomes hard to process, but you can shrink the data down without losing much information. Random projection is a clever trick that projects high-dimensional data into a lower-dimensional space using a matrix filled with random values, typically just positive or negative 1. Surprisingly, The simple method keeps the distances between points nearly the same, thanks to the Johnson-Lindenstrauss lemma. This lemma guarantees that if you choose enough dimensions, you can reduce the data safely. So, with just a bit of random math, you preserve the shape of the data while making it much easier to handle. So, when you have a matrix with the vectors after applying SimHash, you multiply it by another matrix of positive negative ones, which has a shape of original dimension times target dimension. As a result, you reduce the dimensionality of each of the cluster vectors to a target dimensionality you want to have per cluster. As simple as that. Random projection can keep the mean similarity error really low, even if you reduce the number of dimensions quite significantly. The chart presents what it looks like for 10,000 randomly generated vectors of 8,096 dimensions each. It's an interesting method, which might be useful not only for Muvera, but also just to reduce the dimensionality of any vectors. As the chart shows, the error remains the same at 4,000 dimensions, 1,000, and it doesn't meaningfully increase until you are close to 100. This means you can significantly reduce the dimensionality of your data while only introducing minimal errors in terms of relative distances. You still have multi-vector representation, yet at this point, it's always a sequence of the same length. Each cluster vector has a dimensionality equal to the target dimensionality of the random projection. However, HNS search needs just one vector, so we simply concatenate them all in an order defined by cluster IDs. At the very end, you get a long single vector representation, but you can control how long it is by modifying the parameters of random projection. At this point, you've probably realized that Muvera heavily relies on random procedures. If you are not lucky enough, the SimHash hyperplane may divide the space in a way so two tokens will be on different sides of it, even though they have much in common. Dog is the only animal that can bark, but by a random chance, these tokens may end up in different buckets. That's why Muvera assumes multiple repetitions of the whole process. That applies to both similarity hashing as well as random projections. The number of repetitions is another parameter of the process you can control. Quite often, you set it to at least 10. Once you repeat the process, you concatenate all the embeddings and that's your final vector. Typically, there is no need to implement that process from scratch, but you can rely on an existing implementation. So let's see how it works in action. Let's configure Muvera for call-pally embeddings in production. You will use casing equal to 6 to create 64 clusters, and random projection will compress each cluster vector from a 128-dimensional one to just 16 dimensions. The entire process will be repeated 20 times. Each repetition uses different random hyperplanes for SimHash and different random matrices for the random projection, creating diverse representations that are concatenated together. This gives us 64 clusters times 16 dimensions times 20 repetitions, which is 20,480 dimensions per document. It's larger than a typical dense vector, but it enables way faster retrieval compared to full multi-vector search while still maintaining high precision. Please notice you explicitly set the value of the random seed. Since Muvera is based on randomness, you do it to ensure reproducibility. All the documents and queries have to be processed through the same SimHash hyperplanes and random projection matrices. Otherwise, they won't be compatible with each other. You can again make a decision whether you want to create the embeddings or just use the pre-computed ones. Now let's apply Muvera to real document retrieval. You will use the same PDF screenshot dataset like in the previous lesson. Those are pages of lecture notes, each encoded with call-pally's multi-vector embeddings. The same helper function will handle loading these pre-computed embeddings or computing them fresh if needed. These embeddings contain over 1,000 token vectors per page, making them perfect candidates for Muvera compression. Time to compress these multi-vector embeddings into fixed dimensional encodings. We'll process each document through our Muvera instance. The process document method handles this complete pipeline: SimHash clustering, averaging within clusters, concatenating all cluster vectors after applying random projections, This transforms each page's 1031 variable length vectors into a single 20,480 dimensional FDE. Now let's prepare the search queries. We'll still use the same 3 queries like we did in the previous lesson and process them with Muvera query pipeline. The helper function will load or create query embedding similarly like we did in the previous lesson. Now we can process these queries through the same Muvera process. However, please notice that you are calling process query and not process document anymore, because there is a slightly different way of how we approach queries in the Muvera algorithm. Now comes the exciting part, creating a quadrant collection that stores both representations side by side. We'll set up 2 named vectors, one for the original call-poly multivectors with maxim comparison and HNSW disabled, and one for Muvera fixed dimensional encodings as regular single vectors with HNSW enabled. This setup allows you to directly compare retrieval speed and accuracy between the 2 approaches. Let's insert all the document pages into our collection, providing both representations for each. This allows Quadrant to index and search using either approach. Once you upload your vectors into Quadrant, they are immediately available for search. However, the HNSW graph might still not be ready, and the optimizer might be building it in the background. In production, you rarely care about that, but here we really want to test the approximate search for Muvera embeddings. Checking the collection status in a loop until it becomes green is an easy way of making sure it's all done. Time for the moment of truth. Let's compare retrieval quality and speed between call-poly's original multivectors and Muvera's compressed representations. We'll search with both approaches and examine which documents they retrieve. Muvera should provide significantly faster search while maintaining high precision. We'll define 3 simple helper functions to make our search experiments clear and easy to follow. Let's start with one for call-poly vectors. Each of the helper functions will return results and timing. Then a comparison function will calculate precision and speedup metrics. This separation makes it easy to run each search independently and understand what's happening. The next helper function will perform search using just the Muvera embeddings. Let's test our first query by searching with both methods independently. We'll start with call-poly's original multivector search, which is our baseline, and then run the same query through Muvera's compressed vector, and finally compare the results to see the precision and speedup metrics. As you can see, Muvera was 18 times faster in average, which makes it a good candidate for improving the speed of multivector search. Here is how the call-poly retrieved documents look like. And here is what Muvera was able to retrieve. We are having a look at it because the precision reported for that query was only 40%. Now let's test the second query following the same pattern. Muvera is still significantly faster and the precision is relatively low. If you are interested in seeing the individual results, they are just displayed here. Finally, let's test the third query to complete our comparison. Even though Muvera is again 18 times faster than original call-poly embeddings, the precision of 0% doesn't make it any interesting if you really care about the quality of search. Here is how the search results look like, and you can clearly say that Muvera wasn't really able to find the best matches for our query. Let's calculate the average performance across all queries to see the overall impact of Muvera compression. In average, Muvera is 17 times faster than original multi-vector representations. However, there is an enormous precision loss compared to the original call-poly embeddings. In production, the optimal approach combines both methods in a single efficient query. Use Muvera for fast initial retrieval of candidate documents and then rerun those same documents with the original call-poly multivectors for maximum accuracy. Let's create another helper function. Quadron's prefetch mechanism lets you implement this entire pipeline in one API call. Muvera retrieves more candidates than expected, exactly 10 times more, and then call-poly re-ranks to get exactly n results. This gives you the speed of single vector search with the precision of late interaction models, as running max scheme on a small subset is going to be fast enough. It does not make much sense to run prefetch with Muvera and get exactly that many documents as we want to present to the user. If we use call-poly for re-ranking, then it can only reorder the documents it was given. So if Muvera didn't return the best matches possible, it will just define an order for this suboptimal set. Let's run the same set of tests using call-poly multivectors and two-stage retrieval with Muvera and call-poly re-ranking. We'll start with the first query. You can definitely see that the speed up we got is not that spectacular. However, the precision is slightly better because it's currently at 80% for the CoffeeMug query. The call-poly results have not changed. However, we can expect two-stage retrieval to get a bit better results. And indeed, it did its job a little bit better. Let's test the second query. You are getting better results with every single attempt. You should expect the speed up to be quite consistent, but this time we are getting an ideal precision. That means we are getting the same exact set of results for both call-poly embeddings and two-stage Muvera plus call-poly re-ranking. There is one remaining query that we still want to test. Unfortunately, this time Muvera two-stage retrieval was not able to find any meaningful result, and indeed it's keep returning some random slides that have nothing in common with the query provided. However, we can control the quality of retrieval for two-stage pipeline by increasing the oversampling rate. For example, by setting the oversampling rate to 20, so we can get 100 results to re-rank with call-poly. Let's summarize the results of all the queries. As you can see, the average time spent on two-stage retrieval is still significantly lower than for the entire call-poly embeddings. However, the precision might not be acceptable if you really need the best matches possible. However, we've successfully demonstrated Muvera's practical application to multimodal document retrieval. The results show that Muvera achieves its promise: significantly faster search, while maintaining high precision compared to the original call-poly multivectors. The compressed fixed-dimensional encodings enable HNSW indexing, dramatically improving query latency. The two-stage retrieval pattern is the recommended per-action approach. Use Muvera's speed for initial candidate retrieval, then leverage call-poly's accuracy for final re-ranking. This hybrid strategy delivers both performance and quality, making multi-vector models practical for large-scale applications. In real-world scenarios, with thousands or millions of documents, Muvera's benefits become even more pronounced.